Sorry, I'm checking one last time whether the mic is working or not, because the first video was not recorded, or it was recorded, but the audio was terrible. Okay, this is
Are you
good.
going to share last semester's recordings? I think you mentioned.
Yeah, it's oh yeah, at least the first video.
Okay.
Yeah, I will share it. It's already online, but I need to give you the guys the link. So yeah, I will do that. Yeah, so I'll do that for the first lecture for sure. Yeah. So I wanted to start with just a couple of examples before we get into where we were about CNNs. But anyway, I just wanted to show an example of what's happening in 2024. So this is just something that was released. This is a deep learning model released yesterday or earlier this week. Basically, what you can do is go from text to a video. Okay, so that's so input is a text string and the output is a video. So, I mean, you can see the input prompt, right? Confident teddy bear surfer rides the way in the tropics. So that's the string. And there was some model trained on an insane amount of data. And given that string, the model is able to generate a sequence of images, so a sequence of tensors, these 3D, three-dimensional tensors, and then you stitch them together. That's the video, and so that's the output here. And so they have a bunch of videos. I mean, obviously, they are showcasing the best videos that they obtained, perhaps in their experimentation. This is research quality. This is not like production quality yet. But you can obviously today, if you look at such tools, Adobe and some others are actually integrating a lot of AI-related models in the vision space. So I wonder where yeah, it was just published yesterday, right? So yeah, yesterday. I mean, it was just on social media, so I picked it up. But just trying to show that they use the name diffusion model, which is not there in the current sequence of models that we're going to look at. But one of the most famous ones in the past couple of years is Stable Diffusion, as a company which provided these open source text to image generation models. So you would write a prompt and you'd get an image. I don't know how many of you have tried OpenAI's DAL-E program. Okay, it's very similar. So they're also, I don't know exactly if they're based on diffusion models, but Stable Diffusion, a company which also has these models, they are based on what is called diffusion model. And we'll look at it. If we have time, we'll talk about what is a diffusion model and what's the basic idea behind it. But I just wanted to show this. The second example is interesting. This is actually in the course syllabus. If you look at the introduction, there's some comments about use of copyright data for building these foundation models. I'm not giving credit or some sort of remuneration or some sort of compensation for using somebody else's intellectual property rights or unrelated artifacts. Okay, I'm going to use these words informally, but basically this is an example work that a couple of folks did. Their names are here. Mark Marone and Benjamin Van Turm, and they have basically a way to. So they're basically saying that foundation models, which means that all these large models that big companies are releasing, for example, they claim it to be open source, although open source, it's unclear whether the weights are open source, is the model definition the open source, or the training process the open source part. But nonetheless, it can be difficult to answer this question, which is, has the model already encountered a given example during training? As in, it was this, whatever the model generated, like when you go to ChatGPT or Bard or one of these systems and you ask a question that produces something, is that verbatim present in the training data? Okay, makes sense to check this, especially if the data is was actually copyrighted, like if it's from a book. Okay. So they build a couple of tools which are really good. You should try them. You'll get a sense of what they're trying to do. They do some computer sciencey stuff, which is called sketching, which is a very nice idea in computer science. It's just a very quick way to match things. Okay, so if you have a data set and if you have a query, it's very one of the applications is to very quickly match data to your query to if there's a data point existing in your data set. Okay. So for example, if you look at the pile is a big data set, the stack is also a big data set that was used to train big models. So you can see, for example, I mean, they have 5 examples here and also a preloaded example. So they're just saying, okay, if the model generated something like this, they can actually figure out, they can show a UI where they'll highlight which text and which part of the, you know, which substring in this response, in this response generated by the model is actually part of, is part of the original data source. Okay, so for example, I mean, for this seems, you know, it's like a little bit of match of strings. But you may say, okay, it may just be a so here the UI is such that if you click on it, then it'll say, you know, it'll just obviously highlight the same thing, but also what is the, you know, what is that was part of the data set, for example. So anyway, this is a nice UI that they built to kind of see that if, you know, if your model is just recapping, just producing the same thing in the data set. Okay, so for example, I think for yeah, like for example, if the LLM generated something about Harry Potter, okay, you can see that in this case, you know, it's not, I'm not saying that this is generated by LLMs themselves. I mean, this is just an example text to show that if the text was like this, then they can just quickly point out that, okay, here, this whole string from this to this is actually part of, like if you click on it, I mean, here right now, it doesn't show which book and which corpus. I mean, corpus is this corpus called book 3 in this case. I think, where does it say that? Somewhere it says, yeah, book 3 corpus, books 3 corpus. But yeah, it'll just match that, hey, saying that this is present in the data. Okay, so it's interesting to kind of think about this because they are actually kind of using copyrighted data basically, which is a very and there are actually active litigation going on. Actually, if you click on that legal thing, you can look at the stories related to legal challenges. Okay. Okay, now what I want to do is get back to our notes and kind of recap where we were in terms of CNNs, and then we'll start with today's objective. So I wanted to quickly mention, so we are actually before that, maybe I'll quickly discuss the assignment also. It's on my list. So we are here and we, you know, again, 2 weeks later is our second assignment submission. I know does anybody did not submit the assignment and has not told me yet? Okay, everybody did submit an assignment solution. Okay, so that's good. So you should enter your names also in the group information sheet, which is linked on the left side of the Blackboard, so that, you know, it's not just you submitted and the names are there in that, so, you know, notebook or whatever PDF, but also there in the Excel sheet. Okay, the Google Sheets document. So I'll use that to group you guys on Blackboard. Okay. So what we have covered last time is actually CNNs, which will be part of assignment 2. And what we'll cover today will be actually literally the question in assignment 2, in the sense of there's going to be something called transfer learning and fine tuning that we'll get to. And that's basically the core of one of the questions in assignment 2. There are 2 questions in assignment 2, 2 questions in assignment 3. And so one of the questions in assignment 2 is about transfer learning, okay, which is going to be the agenda for today. But before we get to the agenda for today, I want to quickly talk about assignment 1. Any questions or challenges with assignment 1? It's not supposed to be complex, but I wanted to quickly check with you guys if there's anything that's not clear.
First question, doing on the Python is very complicated, and
no, you don't have to do it by Python. I mean, you could just, drawing means, I mean, nowhere does it say you use it Python, right? I mean, sure, it says done in a solution, but you can take an image and just open that image in a cell in your notebook also.
the same.
Okay, I think most people would do the same.
And the same thing with the, I think, question number 5. So there was some confusion between the MNIST data and the fashion
Yeah.
NIST data. So
Yeah.
both are different actually. So
Yes, they are
what we
different.
do, means we have to make a neural network on both of them or any of them.
No, slash means or.
That was little bit confused.
You can just ask me actually.
I don't have that much time to.
No, you can just select this and say raise an issue, right? I mean, I don't know if this lets you do that, but you can just, okay, here it's rendering the notebook. But you can just create an issue here, right? And just leave a comment and move on, right? Just new issue, assignment one, what is the issue, and just move on. Yeah. I mean, you want to be efficient, but it's good to raise it in case other people have the same issues. For example, I can tell you last semester, PyTorch version changed and there was a lot of battle with some object that was not, because of, the object's API changed in terms of methods, and there was a lot of confusion, which, we could have avoided if somebody told me beforehand. So I'm just telling you that it's good to raise these things either through issues here or just email me and I'll kind of take care of it. Yeah. Sorry, let me come back to assignment one. So backdrop is easy. Gradient descent is what we already saw. Like if you wanted, you could have used the PyTorch example that I showed with simple linear regression, where I was just showing you how to use PyTorch to kind of do simple linear regression, the slope and the intercept. Here it's very similar, right? It's exactly M and C that you're learning. It's just that the data set you are generating the data set. And in the second part of the question, you have a quadratic function. That's all. I mean, it's a quadratic function, quadratic in X. Yeah, but you are still learning these coefficients, M1, M2, and C. So, and then you have a slightly different function here, tan h, which we saw tan h last time. Question 3 is just writing a function. So it's not really, you're not even testing the function here. You could write tests if you can, but it's just definition of a function, okay? 4, it's the same data, the data set that we saw in the lecture. And it's doing a few more things that was not shared not there in the example data set, like test range split and multi-class logistic regression and L2 loss was already covered in that script. You could use the script, you could also do in some other way. Like you could use like scikit-learn or something to do this as well, right? But basically this question is about sensitivity analysis of, okay, what if I change this? What if I change that? Learning rates and, basically learning rates in one question, number of iterations of gradient descent in the other question. Sorry, the same question, I guess. Plotting. So you should have tried at least matplotlib. There are other libraries also you could have tried instead of matplotlib, but something like that, right? And then just the coefficient regularization coefficients. How does that influence performance? I don't know. So there's actually a link on today's lecture goals, which looks at overfitting versus underfitting. I know this analysis here. Like for example, if you chose a huge regularization parameter, that you would be massively underfitting the data, because you're really preferring certain. You're really preferring. Sorry, you're adding a lot of bias, and so your model is gonna potentially underfit that data. Okay. I mean, first of all, linear model is already bad here, but yeah, and also the impact on a different test range split. So if you have lesser data, does it influence anything? And the last question, fifth question, is mostly just a trying of Keras and TensorFlow. Previously, actually, I should have added potentially also PyTorch because that's what we're going to use, and that's the examples I'm showing in the class. And yeah, one of these data sets. And today we'll see an example of MNIST for transfer learning, which we'll get to when we talk about it. There seems like a question online, or okay, it is audible. Okay. Yeah. Okay. So the first assignment is really a warm-up. I can, in the sense of hopefully, it's the second question assignment and the third assignment are going to be a little bit more standard because they're going to try to test your kind of familiarity with the canonical models that we'll see in the class, like the CNN, like last time and this time, and in the future sessions, there'll be some canonical models. They'll also be part of the assignment, but it'll not be covering all the canonical models. All the popular models in the assignments, but with a couple of them, you'll be familiar with how to load them, how to train them a little bit, how to define them, and how to prepare your data, which is going to be challenging, depending on the data modality. With images, which is going to be part of assignment 2, there's going to be some challenges, and with the text, there's going to be some other types of challenges with dictionaries and mapping words to indices and so on. So what I'm saying is that each assignment will give you a little bit more familiarity with handling different types of data. Okay. Okay. So with that, let me actually get back to. Yeah. So we'll continue. We'll briefly rediscuss convolutional neural networks, especially pooling, which I did not talk about last time, and then we'll talk about some ideas to kind of debug a trained CNN. Okay, so we're not training now. We're just saying, okay, if we had a trained CNN, if you wanted to understand how to debug it a little bit, there are some ways to attack. Some of them not that powerful, some of them interesting and very intuitive. So we'll see a few ways to understand like a trained CNN, how they're performing. And then we look at transfer learning. And we'll also talk about some practical ideas that have come into training some highly performant networks. Okay, so those include data augmentation, batch normalization, dropout, some ideas like that. And you don't know them now, but we'll talk about them when we get there. So let's go back. So last time's goal, especially, and we'll kind of look at it again, recap today, is convolution layer is a collection of filters applied to input tensors. And then why pooling helps in reducing parameters downstream. And this will kind of answer it today. Okay, by the end of today's treatment of pooling, you'll get a sense of, yeah, there's going to be a reduction in parameters. Okay. And then for the rest of the lecture, we're not going to hurry through. So we'll go slowly. If we miss something, we'll kind of cover it in the next lecture. One of the goals is to understand how to transfer parameters from which are previously learned to a new task. Okay, which is a very natural idea, pretty straightforward, but it's good to go through that exercise and concretize it. Actually, first, this goal is to how to kind of at least think about debugging a deep neural network. In particular, we'll focus on CNNs only. Each network will have its own interesting ways to debug them. But for CNNs, there's a couple of lines of attack that we'll discuss today. Okay. I'm saying different engineering tricks, but different ideas that have emerged to kind of improve the training process. One of them is batch normalization, the other one, which kind of does regularization, it's called dropout. So we'll kind of understand what these ideas mean. So it's a bit of, there's no coherent like reasoning for why these ideas are the most important thing to learn, but they are actually helpful to train your network when you add depth. When you add depth, there's so many nonlinearities that things saturate, things die, as in ReLU nodes will kind of will not pass the gradients back, or sigmoid nonlinearities will not pass the gradients back. So a lot of things like that happen, and they happen very frequently. And one of the important, a lot of effort was spent for a good part of last decade to kind of train these networks, learn good heuristics, and some ideas emerged out of that. And we'll look at a couple of ideas. Okay, that's what it's about. All about training deep networks, okay, beyond two layers, 3 layers type situation. And yeah, and one of the ideas is related to data. It's called data augmentation. We'll look at it. It's also a simple idea, but helps immensely for image data sets. Okay, so let's actually so I want to recap CNNs, but I'm thinking maybe I'll directly jump to this and see how that works. This is a link actually there's an older link available in the slides. I'll show you when we get there. It's like 5 slides after, in the new deck, in lecture 3 deck. But I wanted to quickly show that. So this is a visualization by a researcher, Adam Harley. So what it's showing is a CNN. Okay, so how is that showing a CNN? Let's draw a number here. Okay. So what is this visualization doing? It's just showing a deep neural network and a bunch of the information about what's happening here. On the left side, you're seeing what is the input. Okay, it's the input is going to be a black and white image, so it's not a color image. So input depth input depth is 1, and some drawing related stuff. And then at the bottom on the left side is just saying what the predictions are. Okay, the first prediction is 7, second prediction is 4. What does these predictions mean? And also there's a scaling down of this drawing because the network is small, so it only takes a small, like think of MNIST, right? MNIST has only 28 cross 28 pixel images. If the original image was 400 cross 400, you have to somehow shrink it. Okay, that's called downsampling. And we'll see that idea in pooling also. And where did these two come from? This is just think of, we had a network, so you can see at the top, there is a list of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those blocks represent, and the coloring of that block represents what the prediction is. So you can see that the 7 has a bright color and everything else is like a dark color. So yeah, guess is 7 for this one, this input. And second guess is saying 4. We can't really make out why 4 is the second guess, but maybe it has some probability better than the remaining 8 numbers. Okay, so that's what's happening on the left side, and the right side is all the layers that are available. So we can hide all these layers, right? So let's keep them on for now. And let's now understand this diagram from bottom to top. Okay, this is just giving you a sense of the full network. And so the bottom is the input layer. Okay, and maybe I should now scale down to, yeah. And then we have a output. Okay, so we have 1, 2, 3, 4, 5, 6. Okay, we have 6 2D activation maps that were generated. Okay, so the first layer is actually a con layer. It has 6 filters. Okay, 6 set of filters, and it looks like the filter stride and padding and all that is such that it produces this size, which seems like the same size of input. Okay, so think of the filter as 3 cross 3 cross 1, and stride is 1 and zero padding is 1. So you get the same size as the input, in terms of width and height. Okay, and since there are 6 filters, you get 6 bread slices or 6 2D activation maps, and so you put them together, you have a output depth of 6. So you have a 6 depth tensor, but width and height is the same as the input. Okay, that's at this level. Okay, this is the output of the con layer. At this point, you would have already done the nonlinearity also. Okay, so these are just the filter outputs currently of a trained network. We are just seeing the performance of a trained network here. Now let's talk about what's going on above. Okay, so this second layer, which we're going to talk about, it's called a pooling layer. Its objective is to shrink the data. Okay, so its objective is to shrink the data in the width and height dimension. Okay? So for every 2D activation map I generate, I'm going to try to divide by 2. So if this was 100 pixels here, I'll make it 50. And I don't know how many pixels there are, but half of those pixels will be remaining. Okay, so it's like decreasing it's like downsampling. You're decreasing the width and height, but keeping the number of depth of the tensor the same. Okay, and we'll see an example in the slide also. I'll recap this. Yeah.
Like specifically half for this particular problem?
Yeah, in this is an illustration of an example network, and they're just doing half here. Yeah, you can do many different things. Yeah, many choices come up. So yeah, in this illustrative network, which has one con layer followed by a pooling layer, and then again there's a con operation. And in this one, there is 1, 2, 3, 4, 5, 6, 7, 8. 11, 12, 13, 14, 15, 16. 16 filters. Okay, and that's why you got 16 activation maps. So it's a depth of 16 and width and height is whatever this is. It seems like it's 12 or something. Okay, 12 cross 12. And then again, shrinking, downsampling in the width and height dimension. So you get one smaller square per activation map. And that's again a pooling step. Okay, we'll recap pooling step through some numbers visually in an example in a second. Okay, once you get here, then you're done with the spatial arrangement of neurons or spatial arrangement of numbers. Okay, at this point you're saying, okay, I'm gonna just vectorize all this. Vectorize all this means one below the other. You just stack the columns one below the other. You get a really long vector. Okay, and then you just apply a fully connected, feed forward layer. Okay, so you're going from a vector, a really long vector, to another vector of certain length. Okay, that's this vector here. Okay, and the intensities are just showing, okay, well, the number is large or small or something. Okay, and then so there's one transformation. So there's a one W comma B matrix, W matrix and a B vector here that characterize this. Okay, and then from here to here there's another W comma B. So there's two fully connected layers. Okay. This one is clear, right? This is a very huge vector to another huge vector. So that's clear. And then from that vector, the last step is again a W comma B to go to the output dimension. And outputs are, we only have 10 classes here, 0 to 9 digits. And so they're 10 class output. So the last W matrix should have the number of rows, for example, to be 10. So that's what this illustration is showing. And it's not just that, it's actually very interesting. So you can see what each neuron, so this neuron, this filter is looking at this part. Okay, just to kind of give you a sense of, so on the same neuron here, we'll also be looking at similar region. Okay, if you pick the same neuron, it should pick the same region of the input. Okay, and this shrinking downsampling is also showing which, because if I have 100 cross 100 and I need to get to 50 cross 50, that means every basically 4 numbers get changed to 2 numbers. I mean, we'll look at an exact computation in a second, but here it's showing that if you wanna, it's basically some sort of averaging of 4 numbers to get to 1 number here. Okay, we'll see that step in a second. Yeah.
Can you explain the first part again? Like from the black and white 7, how did we get the blue part?
Yeah, this is one filter. Since the filter, this input doesn't have a depth, this filter is just convolving. So this filter, so we're not seeing the filter here. There's a 3 cross 3 filter, which is convolving from the top left to all the way to right and back and forth. And this is the output of that filter operation. The filter size is 3 cross 3. What's it?
What are we exactly trying to achieve from this?
What are we trying to achieve from this layer? From the con layer?
Yeah,
Detecting patterns.
Yeah, like one by one, like what are we trying to achieve by this step?
What are we trying to achieve by each layer? I mean, you get to stack these Lego blocks any way we want. Okay, so it doesn't have to be con followed by, why did they choose pool here? They could have dropped the pool. Yes, they can do many different things. They just chose a pooling layer. They just chose another con layer. They chose another pooling layer. You didn't need to do all this. You could have just gone from this, vectorize this and say, I want to just use a feed-forward network also. So now what is the value of con layer? Is because if the filter is detecting some, horizontal edges, then that filter can detect that irrespective of where the edge is, right? Because the filter is striding through the whole input image. Okay, that's spatial invariance, like where the object of interest is to classify something as like 7. For example, instead of writing 7 here, if I had only put a 7 over here, maybe it would still classify 7. I mean, we can check, you can refresh and do it. But yeah, filters are more about like spatial invariance and sharing of parameters to detect patterns. Okay, you don't have to interpret these patterns by themselves. And in fact, you'll see that one of the ways to debug CNNs, you can't really interpret patterns. Okay, here maybe you can. It's just the first layer, and so input is kind of, you can see a 7-ish type of looking thing. So maybe you can interpret a little bit, but once you get beyond, like you can't really say what's going on over there. Okay.
So that dimensionality of our input image will be lower than the dimensionality of the filtered or it's equal.
No, the input image is here. It's something 48 cross 48 cross 1.
48.
I mean some depth. I mean I don't even know if it's 48. It could be 24 here. But anyway, some 48, some square 48 cross 48 cross 1, and the output is because I have 6 filters, each one operating on the input, same input. Each one is producing a 2D slice, and 2D slice turns out the slice here in this illustration is the same. Okay, that can only happen for certain stride and certain zero padding. Okay, you can look into slides from last time. It's just if you have a 3 cross 3 filter and you're striding one at a time, one step, and if you have a zero padding in the input, then you'll get the same size output. That's just you can verify that. Okay, if you did not put zero padding, if you took 2 steps to the right every time, then you will get a smaller tensor here, right? So that's it. So it's not like, so there's a collection of numbers here. It led to more numbers, that's true, but each one is like an output of a different function, right? Different filter. So sure, it's the same input, but 6 outputs were generated because 6 different filters or functions were applied. Is that not clear or confusing?
No, I'm a little bit confused that if we make a model and in the end we don't have a sufficient input value, then it may sometimes leads to our model discard. Means won't work. So we have
it might not guess 7, for example, if it's confusing, or if somehow we only choose 2 filters here and we expect it to work, maybe 2 filter network is like very small and it's not fitting to the patterns in the data. It could happen.
So our output layer should be between 0 to 9.
I mean, you're classifying 10 classes, right? This is like MNIST basically. So you have 10 classes.
So last layer will have 10 inputs.
10 outputs.
10 outputs, sorry.
Yes.
And before that,
you get to
on
choose.
our side.
You get to choose, right? You did that in assignment 1. How many hidden universe?
And a little bit confusing. So, and we choose another input value and then choose the performance.
Another input value. Yeah, you get to choose whatever you want.
In that assignment, it's 28 cross 28. 94.
Yeah.
And we are inputting all the feeding all the inputs.
You're vectorizing it. Yeah, you're not doing a CNN there.
So we
That's
can
just doing
change
it.
that input value from 784 to maybe 1000.
How?
That's why I'm asking that how can we
But that's not related to this, right? This has nothing to do with increase. You can upscale and downscale your images. Okay, that's a completely different, unrelated pre-processing step. Like you had a 28 cross 28 image, you can say, oh, I want to have a 14 cross 14 image by just downscaling, that pooling idea. That we'll just see it in a second with some numbers. So we can change the numbers of pixels in an input. Yeah, but the 784 dimensional vector, now if you want to make it 1000, how are you going to make it? Is unrelated to the model specification. That's an input variation that you're introducing. How do you change the input size? You can create some random functions and fill in some extra numbers.
Layer can have 1000 inputs.
Yeah, inside the model specification, you can specify the model in any way you want, right? It just has to match the input dimension and the output dimension that are kind of predetermined. Except for that, inside you can do whatever you want. Yeah.
I'm
Yeah.
curious about one thing. We have used in this, like there are 2 fully connected layers in the end.
Yeah.
So, like, is it to decrease the vector size to predict, or just for the
It's just model richness here. I mean, if you did not use 2 instead of if you use 1, it'll be less complex model. So I don't know if it would capture all the patterns. That's all.
What I am asking is, just consider that if in any program, not specifically.
Yeah.
For example, if we are using one fully connected layer in the end.
Yeah.
So, if just particularly this example,
Yeah.
considering what exactly why they use 2, but if we are using 1, then also it will be able to predict 2. Like not maybe the accuracy won't be the same.
Yeah, it may or may not. Yeah, you can use 1. You can also not use a fully connected layer. You can use a COM layer also. How? Why don't you have a filter which is let's say 3 cross the length of the input? It can only slide once, right? And if it only slides once, it's going to produce 1 number at every location. So you ensure that the stepping or the sliding is such that you only get produce 10 numbers. Then you only get.
Will you be able to predict in case like R7 is not exactly particular, like exactly written as 7, maybe.
Yeah.
Okay.
I mean, I'm not saying if your input is noisy or if it's a little bit different, it's just like any other model, right? It might fail. Yeah. And that's where we'll talk about how do we know whether the model is doing well. We'll talk about that in a second. Yeah. Well, if you already have a trained model and the question is, what will it do if the 7 looks like a 1 or something? We'll see in a second. Okay. How can we get a sense, post hoc diagnosis of a trained model, like a CNN model in particular, we'll kind of understand in a second. Yeah. Any other question? Okay, those are good questions. But let's see. I don't know where we are. Okay. So this is what we saw. So the filter operation in the con layer is if you had a depth of 3, and in fact, that's what was happening. I want to quickly show that in that illustration also. For example, this con layer here, actually, it's not a good illustration because this con layer is only showing like, okay, this takes the, this filter here, the filter depth should be 6 because each filter here, even though it produces one 2D activation map, its depth is like 6. So it should have also arrows all the way there and all the way there. It's not well shown here, but I just wanted to point that out. Okay, so that was the computation here with if the input depth is 3 and you have 0 padding and your stride, if you have 3 cross 3, you have 2 filters. Here we're just showing the second filter operation to produce this number. Okay, you can go back and check whether this is you understand the computation that's happening. Okay, so here we're just showing that if we are going to look at the second filter and we want to understand how this number came about, then we have to look at this at the top left, this at the top left, this at the top left, and then multiply element wise, sum them together. Okay, so multiply element wise, sum them together, there'll be one number, and one number. Sum them together, add the bias, and then that will lead to this number. Okay. So just to kind of, this is the computation. It's just a linear computation. Okay, this is not, although we're calling it a con layer, it's not doing anything complex. It's a linear computation. Okay. Okay. So let's now talk about the pooling layer. Okay. So we will just wrap this part up. This is the last part of the previous slide deck. Pooling is very vastly more simpler. It's all its objective, our objective in introducing this layer, we haven't calling it layer, but it's really a very simple operation. We want to just reduce the spatial size, okay, using some simple function like a max operation or some averaging operation or whatnot, okay. And we operate it independently for each depth slice, okay. So we only focused on, and there's just a choice, okay, heuristic choice. And we want to focus on reducing the size of the width and the height dimensions and keep the depth the same. So how do we do that? Here's an example of what we want to do. So let's say your tensor at some point in the processing happened to be 224 cross 224 cross 64. Okay. So 64 is the depth. Then we just want to change it to 112 cross 112 cross 64. So we keep the last dimension the same, just a heuristic choice. The depth dimension is the same, and we want to just shrink the height and width. So this is what you would call downsampling. So you have each slice maybe looks like this, looks like this means just each slice is a matrix. You can always visualize a matrix by its intensities, and you just have to downsample it. Downsample means reducing, shrinking the width and height of the matrix. Okay, yeah.
And then in terms of just since we go from 224 to 112, it's arbitrary. That was happy you can buy any amount, right?
Yeah, you can do divide by 3 also. Yeah. So, for example, here's an example of what is called max pool. And if you had a 4x4 image to get to a 2x2 image, you just take a max of these numbers, max of these numbers, max of these numbers, max of these numbers. Okay. That's called max pool. And average pool works the same way. You can take the average of 5 plus 6 plus 1 plus 1 divided by 4. You can also take a min. Why these specific operations? Obviously, average is a linear operation, but max and min, for example, would act like some sort of a non-linearity. Okay? They will have their own non-linearity because they're a function which is non-differential. Yeah, I mean, max ReLU was also non-differentiable. It's only non-differential at 0. It's differentiable everywhere else. These guys will also be differentiable most places except for a few places. Okay. But yeah, this is an example of pooling. It's just some sort of averaging, or some sort of summary statistic of this number. Okay. You can just think of loss of information. There is some loss of information happening here. Okay. And why do you want to do this? Just the reasoning is pooling is applied to kind of keep the number of numbers, to not let the number of numbers explode as a function of, as you're processing more and more, you don't want too many numbers. You want to kind of, because it turns out in this CNN, for example, if there are 6 filters, 3x3 size, 6 times 9, okay, that's the number of numbers here, plus let's say another 6 numbers. So less than 100 parameters here. Okay. Here, let's say this is average pooling, no parameters, or max pooling, no parameters. Here, again, let's say there's a 3x3 cross whatever 6 as a depth. So a few more numbers, maybe thousands of numbers here. But here, if you vectorize these guys, each neuron will be associated with hundreds of parameters, each single neuron. And it looks like there are like at least maybe 100 neurons here. So 100 times 100 is already like 10,000, like it's reaching like an order of magnitude more number of parameters. So what I want to say in summary is that the parameters in the con layers kind of are minuscule compared to the number of parameters you'll have in these layers at the top, fully connected layers.
You just mentioned like to control the number of
numbers. Yes.
Not to like explode. So like, do you refer to gradient?
Yes. No, not gradient explode.
It's separate.
Yeah. Here, for example, the reason why, if you think of, if we did not do max pool, you would have a really like maybe almost 2,000 numbers here. And if you did max pool, maybe you had 1,000 numbers. So if you had 2,000 numbers per neuron, because each one of these is a neuron, like if you remember from fully connected layer, then you have half the number of parameters, right? So it's just control of the number of parameters. Yeah, nothing else going on. Yeah, I mean, there's some networks of these recently are not even putting a pooling layer. So, but this is not the predominant thing. Mostly people do this because control the network complexity. Okay. So there are some places where they increase the complexity, some places they decrease the complexity. It's just art. Some of this is art. Okay. Fully connected layer, we've already talked about it. So I'm not gonna. And there is another implementation of a CNN in the browser. I'm not going to look at that because we just had a CNN illustration in the browser. So any questions about last lecture? We looked at a feed-forward neural network. I mean, we defined what a feed-forward neural network is last time, and we saw that it did better than linear classifier in that 2D example. And then we switched over to, okay, a new data set. Let's talk about images specifically. And we defined, pretty much layer by layer, like how does it work? How does the parameter sharing happen? Although we have looked at mechanically from layer perspective, neuron perspective, and all those details, at the end of the day, at the layer level is just linear transformation. Okay. And this con layers, somebody asked like why are we doing con? Is because of the spatial invariance feature, filters looking at local, a local region, okay, which is not something that you could capture in a feed-forward layer. In the sense, the feed-forward layer is looking at everything, okay, whereas in the fully connected layer, in the con layer, you are looking at region by region. Sometimes it's an advantage, sometimes not. And then it turns out, like as I said, if you have a con layer closer to the output, then each layer activation map, even though that filter is only looking at immediate preceding tensor and a small part of the immediate preceding tensor in terms of width and height, if you just backtrack all the way to the input, it's actually looking at the full image potentially. Okay, so there's some sort of a blow up happening if you just backtrack what all led to that neuron's output. Okay. I just want to kind of briefly mention why neural. I think this is something, this is just my kind of very short description of why neural. So there was a name called perceptron used for this type of function, which is just a thresholding function on a linear function. Okay, so you had a linear function and you just compare it to threshold, and you would say, its its output is 0 or 1, some sort of binary classifier, and that was used to be called a perceptron. Okay, and all these were kind of related to the idea that there is some sort of input value, and you compare it to a threshold, and that would signal kind of trigger the output of the neuron. Okay, so for example, the sigmoid, like the sigmoid function like this would kind of say, oh, there's a probability with which the neuron would trigger its upstream neurons and its downstream neurons or whatever. Okay, so there's some analogy here, but it's not really, they have deviated so much that artificial neural networks and biological neural networks are not really anything similar. Although people are trying to get inspired in terms of how to do gradient descent, inspired by biological mechanisms sometimes. And there's also trying to interpret biological mechanisms as gradient descent. So there's some work that's going on. Okay, and finally, convolution, part of convolution neural network. This comes from convolution operation signal processing, which is a field in electrical engineering or in general engineering. It's just a matrix product, so it's just a linear transformation. Okay, it's like Wx plus b, except the W is more structured. Okay, and there's going to be reuse of entries in the W matrix. So it's not a W matrix with all parameters being unrelated to each other. Okay. In particular, if you want to see, here's like this convolution operation versus a autocorrelation operation. Just to kind of get a feel for like what is something that I know. Autocorrelation is something that you might have seen in Pi70 or some of you might have seen before. Autocorrelation of two functions just means you want to say kind of element-wise multiply the function. Autocorrelation is parameterized by some sort of a delay, okay, one-dimensional number, and it's just asking how much do the functions look similar to each other. Okay, so for example, let's only focus on this area, f times f here on the right side. Okay, so this black line that you're seeing is the autocorrelation output of what is the input is this function. Okay, step function. Actually, it's two steps here. So you're just computing, the function times function basically. Okay, so you're keeping one of the function fixed, and you're saying, okay, if I multiply with a shifted version of the function element wise, and then add them up, I get a 0 because they're not overlapping anyway. Okay, in the sense when this copy is non-zero, the other copy is 0, so that time 0 is, that's why this is zeroing up. Okay, but the moment they start overlapping a little bit, like for example, there's some overlap, and now you start seeing an upward, like there's some non-zero value. Okay, and the overlap is a maximum. That's when the output is a maximum. So if the overlap is maximum, then every number times number, sum them up. That's the highest number. And now the overlap decreases as the one function keeps moving to the right. So if the function, so one copy, if it's the leftmost, then overlap is 0. Start overlapping, maximum overlap, and then when you go to the right, you're overlapping less. Okay, that's a parameter of the autocorrelation function. So autocorrelation 0 should be the highest. Okay, you should correlate with yourself the maximum. So that's autocorrelation. Okay, and convolution is exactly the same idea for two different functions. You could do autocorrelation. I mean, you would not call it autocorrelation if it was just two different functions, and that would be called cross correlation. Same idea. Instead of f times f, there's a different function, but it's exactly the same thing. You keep moving the g from left to right, keep f fixed. It's exactly the same location, just the g that is moving, the red thing that is moving from left to right, and how much ever is overlap, that's a cross correlation function. Convolution is exactly the opposite, where if you are given f and g like this, you would flip the g first. Flip the g in the sense that if this is peaking here, then you would have a different one which is peaking over there like this. Okay, just a mirror image, and then exactly do whatever is happening here. And so that would be called convolution. Okay, it's just a naming given to a certain linear operation. Okay, this is a linear operation also. So I would say, you can look at Wikipedia or use ChatGPT to kind of understand a little bit more about convolution. Any questions here? I just wanted to kind of mention that the names are derived from some historical precedents. Yeah. So what we want to do next is tackle three things, and we may not have time to tackle everything, which is okay. First bucket of items is exactly the type of question that was being asked. So if we have a CNN or some model that we train, how do you know it's actually good? Like, what if I put a slightly different 7? Is it going to classify it as 7 or is it going to classify it as a 1? Okay. To ask those sorts of questions is just trying to understand how well does my CNN work, and those types of questions. Okay, how well does my model work? What is its failure points? Things like that, right? So I'm just calling it visualizing CNNs because they're actually not they're qualitative methods. They're not quantitative methods, and so it's a little bit visual inspection and manual checking of things. Okay. The second bucket of things, which is related to assignment 2, first question, is transfer learning. It's a straightforward idea, but we want to kind of go through and understand a couple of variations of that. And there's also another new idea there. It's not really transfer learning, but it is an idea related to fine tuning. It's called low rank approximation, LoRA. I don't know if anybody has heard of the acronym, but we'll visit that also. It's not in the slides, but we'll talk about that. Okay. That's the second bucket, just to kind of leverage pre-trained models and adapt them to any domain-specific use. Okay, that's the use of the second bucket. And the last bucket is, I would say, some training tricks or some ideas that help you train deep neural networks and really control the gradient properties and so on. Okay, so it kind of helps you by shifting the numbers. Like, for example, if you think of z-scores, right, you kind of shift the number, subtract the mean and divide by the standard deviation or something. So those are just shifting the numbers, but those operations turns out they help with gradient propagation. Okay, that's what we'll see in the last bucket. So we'll go through one by one. It's like there's some question online. No. Yeah. So I'm not going to recap. This is like we have seen it several times. This is just looking at the parameter count. So if you had fully connected network here, it turns out you need 3 billion parameters compared to some lower number at the top. So it's a slide that you can just check that why there's a parameter reduction. If you use one network. What is it? What is meant by zero padding? Is the question. Oh yeah, zero padding is like how many like at the border of an input tensor are you going to add zeros to the left and right and top and bottom? Okay, so I think we had this. It was a little bit of a detail that I might have gone through very quickly. Let me just show you that slide. Yeah, for example, here. So in this example, this gray part was not part of the input tensor. It could be input image or it could be some intermediate tensor, but the gray part was not part of the input tensor, and we added these zeros, and that's why it's called zero padding. Okay. And you'll see zero padding somewhere else also later. I'll mention that. Now, that's because that's in the text situation where input text, you want to kind of process things in batch. And if you have sentences, they may not all be the same length. And so you'll add some padding to kind of make them the same length and then pass it through your model. Okay. That's also padding, but that's something different. Here, zero padding is just adding some extra zeros. Why? Because your filter may be detecting patterns at the edges, and maybe that's important. Yeah. Yeah, and it also helps with like controlling the dimension in the sense that if you wanted a specific dimension as an output, you could add zero padding to kind of ensure that such a dimension is possible. Okay. Stride means how many steps you take to the left. Yeah. So this is just some parameter counting exercise, so I will not focus on it. Backpropagation. We're not going to really think through too much because Conn layer I've been emphasizing, it's just a linear operation. So there's nothing nonlinear there except for the nonlinearity that you would apply once you get the filter output. You could apply nonlinearity on the activation slice. Except for that rest of the previous operation prior to that is all linear. So there's nothing complex about it. It's a matrix multiplication. And then backprop through the pooling layer, if you do max pooling, it's going to be very similar to ReLU because ReLU is like max of 0, x. Max pool will be max of A, B, C, D. Okay, so it's a 4-dimensional function, so it's not easy to kind of see, or what is it will not look like that hockey stick that we were seeing, because you have to think of all the 4 dimensions. But at the end of the day, it's going to be exactly like that. So it is differentiable in most of the places, except for a few kinks here and there. Okay, changes here and there. So that also is manageable. Okay, and anyway, you're not going to do this. You don't want to code it yourself. TensorFlow and PyTorch will take care of these steps. So let's really get into the first bucket, which is I'm calling it visualizing CNNs, which is just really about combating non-interpretability. Okay, there are a bunch of established techniques that you might have seen, especially for linear regression related linear family of models. You could even do hypothesis testing under assumptions about the data distribution. You can do hypothesis tests on the coefficient, saying that the coefficient is being non-zero. Whether you can reject the null or not, right? So you can do hypothesis tests on the coefficients of a linear regression model, okay, under assumptions. So there's diagnosis you can do for example, linear family, not just hypothesis testing, but there are many other things that you can do to understand whether your model is fit. What are the errors look like, error distribution, many different things, not just for linear family, but also some other models like models from scikit-learn family, right? So logistic regression, SVMs, and so on. There are many model diagnostic ideas, many heuristics, which is fine, but there are many ways. Now, how do are there any ideas to kind of do something similar for CNNs? Okay, so we're going to look at some ideas, and this is just to give you a sense of. You can also come up with your own ideas for any canonical model that we'll see in the class. Okay, so CNNs and feedforward networks are two things that we've seen, but there could be many other models. But each one you can think of what is reasonable and helps you understand the model performance. Okay, for text models, these ideas may not apply, but it kind of gives you that sense that, okay, you can come up with your own heuristic to get a sense of what the text model does. Like that data portraits thing, they have, they said, okay, for any input text, I can figure out which element in the training data matched it. Okay, that's not really about training. But you can do something similar, right? You could probably highlight part of the text that is actually kind of leading to a class, leading to a class label, for example, positive sentiment or negative sentiment. There are ways to do that for text, okay? But we're not going to look at those techniques because we've not talked about text at all. We're going to try to kind of combat this non-interpretability for focus on CNNs, okay? Although some of them just extend beyond them also. Common criticism is like nothing is interpretable, right? Like the weights are not interpretable. These outputs, activations or pre-activations, they're also not interpretable at intermediate stages. And the filter weights themselves may not be interpretable. Okay, first of all, the filters themselves, unless it's the conlayer in the first layer, the filter depth could be arbitrary. Like if filter depth is 7, how do you even visualize, are you going to visualize 7 matrices? Potentially, but it's unclear how to do anything here, right? So we'll look at what is some attack points, okay, some ways to understand your trained model. So obviously, first 2 bullet points are just going to be brief comments. You could potentially look at activations. You could potentially look at weights. Okay, that's something you can do for any network. That's not specific to CNNs. But the next 3 ideas are interesting because they give you a qualitative sense of whether your model is, for example, the 7 versus 1 issue is something that you could resolve based on some of these ideas in the later section. Okay, at least a couple of ideas we'll see in a second. Okay, so let's start with the first one. I think this is the tool that we just saw. This is an older link, but the new link is what I showed in the slide. What I just showed. So visualizing activations, does it work? And the short comment is no. Okay, so that's because you could do something like you could, for example, not just the model. If you had the training data and the model, okay, so now you need both. Okay, if you had both, what you could do is, given the model, which means that you have already trained the weights, you can pass your training data one at a time and get a sense of at any given neuron layer or a layer, or at the level of a 2D activation map, or at a single neuron, how many of the input data really made that neuron fire in the sense that gave an output which is non-zero. Okay, because every neuron, remember, if you're going to use a nonlinear, if you're going to use a value, okay, and you focus on a neuron and you pass all the training data and the neuron never gave an output greater than 0, then it's basically a dead neuron, in the sense that that neuron, because that neuron's activation is the output of a max of 0, x, its input probably was always negative or some issue like that. And so it never produced an output which is greater than 0. Okay. So that means it's a dead neuron. So you could do that. So you can pass all your training data, or even one training data point, one image, pass it through and get a sense of which regions of your 2D activation mapper are all 0. Okay. That'll give you a sense of maybe that, those neurons are not firing at all and they're kind of irrelevant to your prediction. Okay. So it could help you do that. So, but it's kind of very hard to do because there are a lot of neurons. So which neurons to look at is a challenge. So here, for example, like first column, maybe you have like few filters or a few 2D activation slices, therefore few neurons to look at. But in the fifth column layer, the moment you have like, I don't know, here 64 maybe 2D activation slices, a 64 length filter depth, and it's just too many, right? How do you even think about how many are? You can count and say maybe counts are useful, but it's kind of very hard. It gets very messy. Okay. Same thing with weights. It's very hard to visualize or do anything with weights. Of course, the first column layer, since the filter depth is 3, so you can think of that as an image, and so you can plot them. You can do an I am sure or whatever, and you can look at the filter weights. Okay, it's going to be looking like 3x3 or 7x7 or whatever is the dimension of the filter. But the moment you go higher, you will have to look at per image, okay, per slice of the filter, which means you are just looking at the 2D. It's just an image of you just have matrices and you're just visualizing the matrices by looking at the intensities. Really not very helpful. Somebody did that effort and they're just showing it here, but it's very hard to kind of interpret anything. Okay, so here the bullet point just says that, okay, if the patterns here look very messy, like random numbers, like like these are not random numbers, but you can imagine like a completely random numbers. Maybe it helps you think about, or maybe you should train more. But having patterns like this is no guarantee that you actually train well. Okay, this is just like a necessary but not sufficient and sufficient type of condition. Okay, so you do want some non-noisy patterns like this, but just looking at this doesn't mean you have kind of done well at your CM. Okay, because anything you do reasonably well, you will have patterns like this. Okay, so not very helpful. But these are comments not just for CNN. So any feed-powered neural network, anything else, it's very hard to kind of appreciate both the activations and the weights. Although people do look at activation statistics, okay, like especially the dead ReLU part, it kind of helps a little bit. May not be useful for interpretability, but at least diagnosing dead ReLU issues, if you're using max whatever ReLU nonlinearities, will help. Now this is a third technique, which is actually useful for at least qualitatively saying whether you're getting you're getting the same classes in the same, you're getting the class difference or discrimination property from your, let's say, multi-class classifier. Okay, you're able to see them. So what do we do with this technique? We're gonna we have a pre-trained network. Again, we'll use training data. Okay, and what we're going to compute, we're going to call them low-dimensional embeddings. Okay, embeddings is a word we are just using for the first time here. We'll use it again for text also. It just means vectors for us. Okay, it's just vectors. Okay, some vector. What vector in particular? If you recall, for CNN, and if you're doing multi-class classification, we have an input as an image, output is a bunch of scores, which further get transformed. But if you think of that that way, then the last output layer, when you generate those 10 scores, there's a W matrix which will have 10 rows, right? Its input will be an output of a nonlinearity of its pre-activation, right? Plus a bias. Okay, so this is what WA plus B would be to get the scores. Okay, so we don't care about the last scores because they're 10 numbers, and we know that one of the numbers being high means that's what the class we are claiming to be. That's the prediction we're making. But we want to understand. I mean, they're anyway linearly transformed at this point, activations at least. So these activations those vectors are what we're going to call as embeddings, just the embeddings, not low dimensional yet, just the embeddings of the images. Okay, so what do I mean? Like, let me go back to that visualization. We'll just call this vector, okay, that vector to be the embedding of that image channel. Okay, some other image in your training data, some other embedding will be there. Okay, or some other, yeah.
Calling that variable or letter A as bit.
Yeah.
And how is it max 0, h?
Yeah, that activation is the output of I mean, it's just a nonlinearity that's separating between a pre-activation and an activation. That activation, I'm just calling it as embedding. I mean, you can take the pre-activation also an embedding. I mean, this is just heuristic. Okay, so at this point, there's nothing determined, very strongly or there's nothing fragile about some of these choices. You could change it to H, and then you will get similar results. Yeah. So basically, here we are just saying that the activation can be considered as a representation of the input image. Representation. There is a deep, there is actually a subfield in machine learning called representation learning. Okay. They think in terms of every complex object should have a representation in a vector space. Representation just means some sort of numerical, I guess, representation, such that properties are preserved that let you do your downstream task well, like discrimination or other things, okay, or next item prediction, whatever it is. So embeddings are like one of the, I guess, words they use in representation learning. So now, what is the low dimension part of it? We just want to kind of now embed, this vector into a two-dimensional space, okay, which is just projection down to 2 dimension. There are many ways to do it. You can do using PCA. You can do it using some nonlinear projection techniques. You can do many different things. Okay. Basically, while we do that, we don't want to do completely random. You could do random projection also, but anyway, we don't want to do. We want to do it such that distance properties is preserved. Okay. There are many techniques which kind of preserve distance properties. Like, for example, if A and A prime were far away in the high dimensional space, like this 100-dimensional space here. If let's say this is A for number 7, and maybe for 1 there's some A prime. If they are far away in this 100-dimensional space, let's say, then they should probably be far away, in the 2-dimensional space also. So that such properties can be preserved using some projection techniques. Okay. For example, so some projection techniques can preserve such things. Okay. So here is an example. It's not very, it's a kind of a very small image, but so the embedding in AlexNet, the one which did really well in 2012, the ImageNet classification. So that's called AlexNet, named after the author. But the last layer before the scoring layer, it's a 4,000 dimensional vector, 4096. It's just a choice of whatever dimension they chose. And then you use here we're just showing a nonlinear embedding technique called TSNE, stochastic neighborhood embedding, to project it down to 2 dimensions. And here we're just visualizing that. Okay. And what are we doing actually? We're going from that vector, 4096 dimensional vector, to a point in 2 dimensions. And then wherever that point is, we are just replacing it with the miniature thumbnail of that image that corresponds to that vector. Okay. So that's how we get this collage. Okay. And what you want to see is basically images of the same class clustered together. Okay. So if you were thinking of MNIST, then all the 7s and all the 1s hopefully are together. Okay. If the 1s and 7s are like mixed up, then obviously we know through performance numbers, we know through log loss by confusion matrices that this is not performing well. But this also gives you a sense of whether things are good, working fine with the CNN. Okay. Obviously, if we it's not, so here, for example, you can say that similarities are class-based and not color-based. Like it could have green color here and green color here, but these are kind of far away because they are they're different classes and the appropriate patterns have been picked up. Okay. Same thing like having a blue here and then blue over there. They're different. But this is all qualitative. Okay, this is just one way to kind of, and this is the. It makes sense for images because everything is visual, and images are color images can be represented in 2D plane. So it's a good tool to use for images. Okay, let's look at the next one, which is an interesting. This is where creativity comes in. So this is an interesting idea, which is now we still have the trained model, but we're not going to look at all the training data. Let's look at one canonical image or one example generic image, and just kind of get a sense of whether the model is performing well or not. Okay. So what are we going to do? We want to figure out which part of the image is leading to a certain classification. So let's say the image has a dog in it. We want to actually ascertain that it's actually the dog related features which are leading to the class dog and not something else in the background. Maybe there's a maybe it's playing in a dog park. That's some features related to the green outdoors or something. That should not lead it to the dog classification. Okay. So what we're going to do, we're going to plot the probability of the class of interest as a function of what's called occlusion. Okay, what do you mean by that? Let's focus on the left column. Okay, let's focus on the left column because the center and the right are the same. So what are we going to do? Okay. So as I said, we have the pre-trained model. We don't have to look at the full training data. We can look at one canonical image. Let's say this is the canonical image. I mean, I'm not saying that one canonical image is enough. I'm just saying that you work image by image. So what are you going to do? It's very similar to the convolutional idea. Here you have this gray patch, which just means that you're going to make those numbers basically, some constant value such that it looks like gray. You put the patch to the top left. Okay. Put the patch to the top left, do a forward pass, you'll get a class, you'll get a distribution, class probability distribution, right? Predicted probability distribution of the classes, right? So when you put the occlusion here, do a forward pass, you get the class distribution for different classes. Look at what was the probability for the true class. Okay? What is the probability? Whatever that number is, plug it in at the top left. Okay. And then you slide that gray box one step to the right. And again do a forward pass. Again look at what's the probability assigned to the true class. That's in the second number. Okay. Again slide the gray box to the right. Again do the same thing, you get the third number. So you basically all these numbers are just kind of representing, if your occlusion was here, then this is the probability which I'm predicting this is the probability I'm assigning to the true class, basically. Okay.
How is this different from convolution? Like the filter?
I mean, there's no filter operation, right? This is just blocking a part of the image and saying what is the probability of the true class. I mean, it's different from convolution operation. There's no multiplication and stuff going on. It's just I'm blocking a part of the image and saying it's very natural, right? I'm saying, okay, if I put my hand here and take this picture and pass it through my CNN, obviously it should not be detecting a dog, right? That's all they're saying. Yeah, I mean, mechanically what we're doing is just sliding and occluding. This is called occlusion. Okay, we're occluding and we're just asking what is the probability we are assigning to the true class. So basically what I want to say is that you can see that the numbers here, it's all red here, except a place where it's saying it's blue. Okay, so red means high and blue means low. Okay, so it's just saying that if I occlude this part, the probability that I'm assigning to the class Pomeranian is still high. Okay,
that's the white background.
Yes, that means that this is irrelevant to me classifying this to be the true class. But if I occlude this part, which is this area, okay, the probability that I'm assigning to the true class is going down significantly. You get the idea? Yeah, what is it?
It was down, but I'm not getting it.
Like
Right, so that means that me occluding this is making the CNN.
You can't see it.
Yes, it can't say that it's Pomeranian anymore. Yes.
I got confused on one part.
Yeah.
What is the use of occlusion?
What's the use of what?
This particular what exactly will be there?
What's the use of this technique?
Yes, I
No, all these techniques are trying to get a sense of whether your model is actually detecting the right patterns to classify X or Y or Z. Okay.
You're just hiding this and passing the rest of it.
Not rest of it, right? When I'm hiding this, I'm just saying I'm just going to change the pixel values. I mean, It's called hiding, but it's just modifying the input image. Yeah.
The model is only saying that, but it's like
No, the model is seeing the full image, except a part of it is modified. Yeah. So you can see that we uploaded this part and it's saying it's not a Pomeranian, or in the sense the probability assigned to the two classes. Now for example here, right? So you can see that the true class is Afghan horn, but there's a lot of noise. Okay, there's a lot of background information, and so you can see that if you occlude here, this area, it's saying it's Afghan horn, but everywhere else is actually messing up quite a bit. Okay, the probability that it's Afghan horn is actually going down quite a bit. And obviously, if you occlude here, it's fine. It's it should do the right thing, but everywhere else it should not be all over the place. In fact, if you occlude this, it's saying it's not Afghan horn, okay, which is not at all expected. Okay, you're occluding the person on the side is not related to the dog, and it's saying it's not Afghan horn anymore. Same thing with the car here. Like you're occluding a tire, and it's car wheel label is not the probability being assigned to the true car wheel label is going down. But if you occlude these regions, which are some car parts, right? It's unrelated to the wheel. You're occluding this part, and it's saying it's not a wheel anymore, okay? Which means that it's picking up some user signals from here. Okay.
maybe the color and black. Variants also gray and black.
Maybe here, right?
Yeah.
Could be. Yeah, I'm just saying that this is a way to, but this is just it's very laborious and hard to do. But you can take some canonical pictures, confusing pictures in your training data set and see if that is, use as a test suit. It helps. The last idea is actually much more complex. I don't know how much bang per buck there is, but basically what you want to do is, again, you have a trained model. Now you're trying to ask some sort of an inverse question, okay? Which is that, hey, I have the trained model. I know there should be 10 classes and 10 scores being produced. What is the most ideal input that would make the score 1 the highest compared to the remaining 9 scores? Okay, which means that you're asking for it's a search problem, which means it's an optimization problem. You're trying to find what is the best input that leads to that neuron fire the most or produce the highest value. Okay, so maximize that neuronal output by changing your input, which is a very, very hard. I mean, it's hard in the sense that you're basically doing what is called a gradient descent instead of gradient descent. Maximizing the output instead of minimizing log loss or cross entropy loss. And in general, it doesn't work. Okay, so if you start with some random numbers, this is how a random number image would look like. Only when you seed the natural, only when you start with some natural image priors, you might get some patterns. Okay, first of all, you can't even see any patterns here, or they're very, very faint. You might get some patterns. If you just arbitrarily try to maximize, the search space is so complex that it doesn't work. Even though the number of numbers here is not too many, right? So if it's let's say 224 cross 224 cross 3, or let's say 28 cross 28 cross 3 or 1, it's not too many numbers. But compared to you optimizing the parameters of the CNN, it's not too many numbers. But still, that optimization doesn't give you a good sense of what's a naturalistic, which we can interpret as, okay, this is the same class, but is actually helping us classify. So, I mean, here we are supposed to so we are looking at a ImageNet has 1,000 classes, right? So one of the 1,000 classes is one of this and one of this, and you can't really make out what's the image. You can maybe very faintly make out. Here's a slightly better classes where you can make out. So it's saying that if this was the input image, I would have goose coordinate. The score for the goose coordinate to be the highest. Okay? If this was this would be the ideal image after you're doing maximizing stuff. This doesn't look like an actual image of a goose, right? But this is the image which the network has been trained such that if this was the image, then that would be the highest class. And this is not a natural image. So this is and same thing with the ostrich situation. Okay? So it's just giving a sense of, but at least, these patterns look like, okay, they're trying to, they look like bird patterns, which is what the network is kind of figuring out through its filters, and therefore it's probably producing a high value for that coordinate. Okay, so there is some interpretability that you can say, okay, even if you might not get a most realistic looking image, at least it's picking up bird related patterns to kind of say it's a goose or it's an ostrich. Okay. Yeah, and you can actually do that at multiple layers, and this becomes very, very hairy in the sense it's not a very it's not a very robust thing, mostly because you need to choose out of the many neurons which neuron that you want to kind of maximize its output. Okay, there's so many neurons, right? I mean, every con layer will have like some input, some output tensor depth. That means there are so many activation maps. Which neuron among them is whose output you're trying to maximize? Okay, and what's the image that maximizes that neuron's output? Okay, here are some just representations of pick some random neurons and see which patterns maximize their output. Okay, so here basically what this slide is trying to show is that there are some lower level patterns that make some neurons in these layers output the highest value, and as you go progress higher and higher, there are more complex patterns that trigger those neurons. Okay, so simpler patterns at the earlier layers and more complex patterns at the later layers that make some random neurons at those layers output the maximum value. Okay, so it becomes hairy, this type of an operation. And one way to kind of restrict this, I wanted to show this because this would be a natural, like on paper, this makes sense. Okay, you have a trained model, which input image would maximize this, maximize the class label, class probability. You can ask, like, on paper, it makes sense, but to execute it properly has a lot of bells and whistles that you need to take care of, a lot of issues that you might take care of. A simpler version of the problem is to restrict yourself to only the training data. Okay, so you're saying, hey, I don't want to arbitrarily maximize across any input image that maximizes the score. Just tell me which among my training data leads to the highest score for the first scoring neuron. Okay, that's easy, right? So it's basically, and that's as simple as saying, hey, among my training data, there's a lot of images of, let's say, people. Which ones? So I don't. Yeah, I'm not saying which image is the. Yeah, I'm not saying, so I'm not talking about classes here explicitly, just an illustration purpose, but all I'm saying is out of the 1,000 images or 10,000 images that I use for my multi-class classification, if I focus on one of the neurons, maybe the scoring neuron or one few below it, I'll always search for what are the subset of these images that are leading to the highest value there. Okay, so this boxes just represent what is that neuron seeing. Okay, so it's not really the boxes just mean that that's the visual field of that neuron. And here is just some sorted order of which type of inputs are triggering that neuron the most. Okay, so you could say that, okay, maybe people's faces, some patterns in people's faces are the ones triggering more than some other unrelated, some other yeah, I mean, here for this neuron, row corresponds one neuron. So for this neuron, people, for the second second example, it's dog faces, but also some other patterns for some reason. For the third neuron, whose receptive field is this part? Spatial field as a receptive field just means what is it looking at. Similarly, houses or trains, I don't know, some other neuron. So this at least restricts you to figure out, okay, what is that neuron responsible for in some sense, instead of like looking at very open-ended images like this. At least you're restricting yourself to your own data set. Okay, and in fact, some variation of this is something you'll do in assignment 2, question 1 also. You're just asking for what images in my data are the most correctly predicted and incorrectly predicted and so on. It's very similar concept to this. Although we're not looking at neuron level. It's basically, we are looking at the score level, which is kind of the last neuron you would think of. Any questions here? So this is at some level, okay, if it's pooling level. And that's why the receptive field is not full image. If you are at the most topmost area, then you would see the full image. Okay, so let's take a break for 10 minutes, and then we can pick up the next bucket of topics. Okay. For the next 40 minutes or so, or 50 minutes or so, we'll tackle the next bucket of things, which is actually the core part of assignment to question 1, which is about transfer learning. Okay, so that's what we'll might not have time to get into these collection of topics today, and we will see if we can cover. If not, it's okay to push it to the next time. So let's get started. It's a in the transfer learning bucket, I want to cover 2 things which are there in this slide and another short slide deck that I've not shared, but I will go over it today also. So that's why we might need 40 minutes or so. So, okay, so what's transfer learning? Transfer learning is basically what we observe with not just today, but it's been a phenomena that's been going on for the past decade. Which was not the case with SVMs and logistic regressions and so on. So there, the models were such small networks that there was no need to transfer from one situation to another situation. So transfer learning is all about, if you have used some data set, trained a model, can you reuse the model weights in some other situation? That's the situation. Just means maybe you trained a model which was doing 10 class classification. Can I use the same model weights in a 2 class classification? Almost the same model weights, because obviously you might have to change the last W matrix, but modulo that, can you do this? Okay, so that's the whole idea. And basically very few people train a deep feed-forward network or a CNN from scratch. Okay, or not just any of these models, but any new models that you will see in this lecture, in this course. Most people will not train it. Okay, they'll try to go to, for example, some model repository and see if there's an existing model that they can adapt it. Okay, sometimes you might just have to. You can use a pre-existing model as is, that's, probably the best case, but in situations where you cannot, then you might have to adapt it and you have to transfer. You have to hope that, some sort of transfer works, in the sense that pre-trained weights can be reused elsewhere. Okay. And so that is against this myth that we need a lot of data for using deep neural networks. Okay. That's precisely because we can do this transfer. I mean, this is transfer that's not possible with some other types of models. And we'll see we'll see 3 approaches, but the last one is related to fine-tuning, but it's not so much about transfer. Actually, it could be done for transfer, but anyway, we'll see 2 approaches. One is feature extraction, the other one is fine-tuning. So those are the 2 things that we'll see. Both are loosely termed transfer learning. Also, again, just like representation learning, transfer learning is a big field in machine learning, which not just means what I'm talking about here, feature extraction and fine-tuning, but could involve some other topics. Okay, so the other topics I'm not going to talk about at all. Something like domain adaptation, like going from domain to domain and trying to reuse models, things like that. They also belong roughly to the field of transfer learning in machine learning. But we'll focus on these approaches. Okay, when we have small amount of our own data, but we want to exploit a pre-trained model that was trained somewhere else, like ImageNet model, then we'll look at these 2 techniques. Okay, they're there's no big distinction between them. You can think of them as 2 ends of a spectrum, and you could actually be interpolating between them depending on some choices. But let's look at the first one, which is a very natural idea, which is that you can just use the pre-trained model as a fixed feature extractor. Okay, what do I mean by that? We just did that actually in the first section when we were looking at thinking about these embeddings and then pushing them down to 2 dimensions. So creating low-dimensional embeddings. The creation of these high-dimensional embeddings in the first place, which was just pass your training data through and get these vectors, that's basically extracting features from that image. Okay, that A vector is basically a feature of that image. Okay, so for example, you can use a VGG or LXNet. These are just names for models that were trained on ImageNet data, and you can drop. Here I'm just saying drop the last layer, but you could drop any number of layers. You could drop the last 2 fully connected layers if there are any. I mean, these, since they are trained on ImageNet, they produce a 1000-dimensional score vector, but you can drop last one or last couple of ones, and then what you get is a network which is not predicting scores anymore. They're just predicting some activations. Okay, because you drop the last weight activations, right? I mean, predicting in the sense they're just generating activation now. Okay, since we dropped the last fully connected layer. So that's what it looks like. Now what you can do is just pass a new training data to get embeddings. Okay, this is just activations of my new training data. That's the only thing I have. I have the pre-trained data. I drop the last pre-trained layer. I have like kind of a chopped, like a part of a network, and I just pass my new training data through this, and I'll just get embeddings of this new training data. Okay. And what do I do once I generate these embeddings? I can forget the original images, and now I have embeddings. I can just do a simple logic regression classification on them if you want. Okay. So is the idea clear? It's just fixed feature extraction. So the pre-trained model is just acting as a fixed feature extractor, which is just extracting a feature vector from the input image. Okay. So these things which we already saw in the previous section, these are called image embeddings. So we can think of the penultimate layer. So this is actually the diagram of AlexNet from their paper. Okay, they did a lot of effort to put kind of how this works. The con layers followed by max pooling, followed by con layer, followed by con layer, and so on. But what I'm trying to say is that these couple of fully connected layers, you can just drop the last one and just think of this 4096 dimensional vector as the embedding for that image, and just use that as a feature vector for your image. So you're not working with images anymore, just creating the fixed picture vectors.
The last fully connected layer that we are dropping out,
yeah,
like 1,000.
That's the output layer.
Output
layer. Yeah, the weights related to the output. You don't have to use this one. You can also use this one. So all these choices, by the way, in the suggestions we're making, they're kind of robust to some of these details. Okay, yeah. So that's it. So you get embeddings, and then you can just you can just use so you can just use that. So if you can create embeddings, then you can ignore the whole network and just, let's say you can just do logistic regression. That's one fully connected layer, is just logistic regression, right? You can just do that. Or if you want to just retain the, if you don't want to do this two-step process of first extracting the embeddings and then doing logistic regression separately using, let's say, scikit-learn, you just want to use, let's say, PyTorch. The way you can do it is you can freeze the weights up to this point. Okay? Freeze in the sense that don't change the weights. You don't do gradient descent on them, basically. So when you define your model, you can just say that, okay, first of all, you have the original model. You're going to delete this layer. Okay. So which you're going to do actually in the next few days, maybe I'll actually show in a demo in a few minutes. The way you define these models is to define a class. You extend a class from nn.module base class, and then you define, okay, layer 1 is a linear layer, layer 2 is a linear layer, layer 3 is a common layer, and so on. Okay. When you say delete a layer, it just means that remove one of the attributes or one of the fields in that class from that object, right? Once you delete it, and then you can create a new attribute or new field in that object also, right? The new field will be such that maybe you're doing two-class classification. Then you can just you can just say, okay, now I have a new W matrix whose input is going to be 4096 dimensional, but output is going to be 2-dimensional. Okay. Now you have a new network. Now you can say, okay, I have new training data, I have a new network, but I don't want to touch the weights of any of these guys up to this point, but I want to tune them, the weights of this last W, B parameters. Then I can say in that, I think we briefly saw that PyTorch code. You can actually tell that the weights of all these layers, freeze them, or you should not be computing gradients for them. Only compute gradients for these parameters when you do a backdrop step. Okay, you can easily specify that, and once you do that, you don't have to do the two-step process of extracting the embeddings and then actually doing a separate logistic regression using some other library like scikit-learn. You could just use PyTorch directly to do this. Okay, and this is exactly what you will do in your assignment also. Yeah. Okay, now let's look at the second approach, which is called fine-tuning, which is just an interpolation, which is just instead of like freezing all the weights and then only training the last W, B parameters, you can say, okay, what if I do one step different from that, which is like I can freeze the weights up to the last pooling layer, and then train the weights of both the last fully connected layers, last couple of fully connected layers, let's say. Okay, you could decide to do that, and that would still look like fixed feature extraction followed by learning like a one hidden layer neural network. It would look like that. But what if you change the learning rates of the weights here, where the learning rate for this guy is going to be 1/2 of the learning rate of this one. So in the sense that these weights change lesser than these weights when you do a back propagation. Okay, you could do that. Okay, and another variation of that idea is why keep all these weights fixed? Why don't you give learning rates to them, but keep the learning rates really low? Okay, maybe even 1/2 of the previous one or 1/8 of the previous of these layers. Okay. So what I'm trying to say is that you can have differential learning rates for all these layers, where the layers whose weights were already pre-trained, as in they are from, let's say, ImageNet training. Those layers have really good weights. You're assuming that they have really good weights. You don't want to change them. You might have to, you're okay with changing them very little, especially the ones which are trained from ImageNet. And maybe when you're getting closer and closer to higher level patterns that are being detected here, you're okay with a little bit more learning rate, and obviously if it's a completely new W&B matrices or parameters here, you're willing to have a reasonable learning rate there. Then that's called fine tuning. You're tuning these finely. And obviously, some parts you can tune not so finely. Okay, so that's called fine tuning. Okay, so it's really just relaxation of the previous fixed feature extraction idea, where you're saying, okay, I'm willing to change the weights, but I'm not willing to change the weights arbitrarily because I know that they are at good starting points. Okay, because they've already been trained on a large data set before. Okay, some ImageNet data or something like that before. Any questions here? So there's just two simple ideas or straightforward ideas. And here's an example of the benefits of transfer, right? So now what this illustration is showing, and we'll go through this illustration in a second, is showing a big boost in performance compared to hand engineered classification from scratch. Okay, so instead of doing transfer, if you just do from scratch, you'll get some performance. But transfer is almost close to, if not better than, this from scratch approach. Okay, so this is a bunch of different types of image-based prediction problems. So the leftmost is object classification. Scene classification is very similar. It's multi-class classification problem. These are all very similar in terms of prediction problems. Some of them are retrieval problems. Their objectives are going to be slightly different than classification. And there are also some detection problems. Detection problems are, you can think of them as classification problems. So most of them are, some variations of classification problems. Okay, and here we're just showing, that if you were, this is actually even comparing with a non-CNN situation, which is this a pipeline of feature engineering followed by an SVM step versus using CNNs. Okay, so first of all, CNNs, we know that they do well. So here's a picture. So here's a legend, right? So greens are best state of the art. CNN off the shelf is the second bar, which sometimes is better, sometimes worse. Off the shelf means like no adaptation as such. And then CNN off the shelf plus augmentation. Actually, did I? Yeah, augmentation is an idea which we have not covered today. We will cover today if we have time, but we have not covered. And then specialized CNN. So actually, yeah, the last one is the red one. This third one, and so now the last one. This I don't know what colors they are. Blue. Blue is the last one. Specialized CNN, and CNN off the shelf is the light color. It is so actually this is not showing transfer learning, right? Actually, I think it is in the sense of this reference. I think they are using ImageNet data first. Sorry, ImageNet trained CNN first. Oh, actually, yeah. Let me take a step back. So this this second pipeline, which is the CNN off the shelf, is actually the pre-trained model, where you're getting the embeddings and then it's just using SVM there. Okay, so remember, I think previously in this case, I was just saying you can do a fully current layer or something, in that study, what they're doing is they're getting the embeddings and they're actually doing the two-step process of once you get the embedding, just do an SVM. So multi-class SVM after you get the embedding. So you could do, I mean, you could actually just do a logic regression, but instead they're doing SVM. That's what they mean by off-the-shelf CNN and representation and whatnot. So what I mean, the moral of the story is they're actually quite comparable to the best of the art by not doing anything, by just using a pre-trained fixed feature extractor and just using a SVM afterwards. Okay. So obviously they're worse in some situations, right? So you just focus on the green bar and the bar next to it. Sometimes it's better, sometimes it's worse. Clearly it's worse here. But it's not. But you get this by just using. You're not training anything on the new data. You're just using a off-the-shelf model. Yeah. So here there were different names, but they're all kind of related to classification. And retrieval is also some sort of classification problem in the sense that you kind of retrieve the right image for a query. Retrieve the right image for the query. So here are some example problems. Okay, so which so far we've been only talking about classification, but I wanted to quickly mention a couple of other problems and how they change the output. Okay, they don't change the output too much. So classification is on the left side. The second panel shows classification plus localization. Okay, or in general, it's called image localization. The problem where you have a single object, and localization just means you need to provide the XY coordinates of the bounding box around it. Okay, a box which bounds that object, and generally you produce a like 2 pairs of coordinates, like 4 numbers. Either you produce XY and then a width and height, or you produce like 2 different coordinates. So basically what you're trying to do is predict the class, which would be the usual classification, but also have an output to 4 more outputs, which are regression targets. Okay, so your training data will have input image, and the annotation or the labels for that would be the label of the object in that image, as well as the bounding box coordinates around it. Okay, so you're doing both combined class prediction as well as the bounding box coordinate prediction. Okay, that's what image localization is. Object prediction is the same idea, just extended to multiple objects in the image. And so you'll have multiple bounding boxes, and they're not the same across images. Okay, so one image will have 2 objects of interest, one image may have 10 objects of interest. How do you deal with that? That's what's captured in this. Makes the problem more complex. And image segmentation is actually again back to classification, but now the classification is not given input image, just classify one object of interest or 5 objects of interest, but every pixel in the image is classified as class type 1 or class type 2. Like for example, so this pixel would be classified as background, this pixel will be classified as part of cat, this will be part of dog, and so on. So every pixel will have its own class label. Okay, that's what a segmentation model is. Okay, and for all of these, they're actually pre-trained models. Okay, for this one, there's a very popular family of models. I think last time I showed you very quickly its graph. It's what is it called, a computational graph or some illustration of it. The family is called You Only Look Once, YOLO. And here there's a very popular model released by a company called Meta. It's called SAM, Segment Anything Model, okay, from last year. So there are pre-trained models. All I'm saying is there are pre-trained models trained on tons and tons of data for even these situations. And you just have to kind of either use them as feature extractors or slightly tune them to your requirement, right? A lot of companies and folks do that. Okay, so let me actually. So I do want to introduce. I mean, that was an aside about different types of problems. I want to talk about one more type of fine tuning in a second. But before that, let's talk about the ones we have seen so far. Which are both actually, as I said, two ends of a spectrum. All you're doing is like pre-trained weights, whether you want to change the weights or not. If you don't change the weights, it's fixed feature extraction. If you change the weights, you're willing to change the weights a little bit, it's some sort of fine tuning. So if you have similar data set, then you could do feature extraction if you have very small data. And if you have in your domain, like, a little bit larger data, then you can fine tune a bit, because you can rely on your own data and you don't have to rely on the pre-trained model, like the ImageNet model. But if your situation is it's a very different data set, let's say you're a medical data set, and ImageNet is nothing to do with medical data, then you will have to either do something on yourself, or you have to fine tune a lot, which is good as saying you just have to train yourself. And obviously, if you're a different data set and you only have small data, you better not use a pre-trained model to do something different. Okay, you can go with a shallow model, which is suitable for a small data set. Okay, and this is also key for projects, not just for image. I mean, especially image-based projects, but it's also important that you kind of rely on pre-trained models. So I mean, this is a canonical a good model for doing this fixed feature extraction or fine tuning, because it's a very, very nicely laid out network, which is exactly conforms to what we have been seeing in our illustrations and diagrams. So this is actually a second place in 2014. And since then, all the models, they actually have some extra, they don't look as nicely as we've been talking about in our canonical CNN setup. Okay, so most recent models, they don't conform to a nice sequential layering of con layers followed by pooling layer followed by fully connect layer. This was the one back in, I guess, 10 years ago, which was doing that. Okay, as you can see, cons followed by max pool, cons followed by max pool, and so on. So this is something that you can download, okay, using Torch or Torch Vision. Not just this model. In fact, in assignment 2, you'll be using a 2015 model called ResNet, which actually won the challenge 9 years ago. And that doesn't have this structure. Okay, it has some extra connections, which we'll talk about when we get there. So this is a very canonical example of how you, AlexNet is nice to discuss, but AlexNet is not really that performant compared to these guys. So this is the one where you drop the last fully connected layer, since you don't care about 1000-class classification. Take this one as a output, or generally instantiate it and then connect a different bunch of weights, and then do fine tuning in PyTorch or TensorFlow or whatever it is directly. Okay. Any questions about these two types of transfer or these two types of tuning? Yeah. No questions. Then let's actually talk about a different. Yeah.
This is like fixed. Like we have two convolution layer, then one max pool.
That's what they define. Okay. This VGG stands for Visual Geometric Group. It's a research group from Oxford University, and they had a network that they proposed in 2014, and they did really well in that competition. Yeah, they just defined it this way, okay, and they decided this and they tuned it, and they were able to do well. But it's not that this is a pattern that you have to follow, right?
No, I was just asking like in VGG, right? So it's like 1, 2, 3, like total 5 times they are doing it, or just
this is not illustration. This is actually the 16 or 19 layer depth that they have. I think 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 16, 17, 18, 19. Yeah, this is the full VGG 19 is their full architecture, actually. Yeah. Yeah, they have a VGG 16 also, which is a little bit less smaller. Those are the two networks that you can also download using Torch Vision, which is part of the PyTorch ecosystem.
And this is like VGG 16. This is just VGG.
This is VGG 19. Okay. Yeah, okay, there's just two models. Yeah, they're just two models. Even ResNet model that you're going to use in assignment 2, there's ResNet 34, ResNet 50, and ResNet 18. They just mean that the number of layers is just kind of shrunk. In fact, you will probably be working with ResNet 18 because the bigger models need more compute and more more effort, basically. Yeah. So we are still on the topic of fine tuning, but one more method which is not there in the current slide deck is the idea of which is actually relevant for other models, which is the idea of it's called low-rank adaptation. Okay, here the person, this is by the author Umar Jamil. They have the slide deck available on their Git location. I'll give you in a second. It's just a nice idea, and what I wanted to show is the example code that they have for MNIST data. MNIST data is something that you've used in assignment 1, so you should be more familiar with it. And we're just gonna kind of see what they do. And the code is also going to help us kind of get a little bit feel for PyTorch, because PyTorch is essential for your assignment 2. Okay. So low-rank adaptation is again an idea for fine tuning. Okay, the same idea, it's related to the transfer learning idea. So you have a trained model, but now you want to do something more. Okay, that's the pretext, or that's the context or problem statement. So what are we doing, right? So this is their slide, so they are kind of introducing how neural networks work. So fine tuning is just about, as I said, right, you're backdropping and you're changing the weights of these layers, except that the learning rates are going to be very small or zero. If they're zero, then you just fix feature extraction. If they're learning rate really small, you're basically fine tuning. That's what you would do. The only problem is that for really large networks, changing all these weights is very hard. Okay, so here, this person is motivating from the perspective of a large language model, which is some neural network. Doesn't look like this. It's just a graphic. But the moment you have too many weights, even if you want to do that fine tuning step that we were talking about in the previous slide, right, when we were introducing fixed feature extraction versus fine tuning, if you have lots of weights, then it's still a hard problem, because you have to kind of instantiate all these gradients for like millions of parameters that may be present. Okay, and you'll see how many parameters there in an example we'll do in Colab. So this person has listed a bunch of problems, which is basically the number of numbers is too many. Okay, so storage requirements and so on and whatnot. So here's the idea, right? It's a very straightforward idea, very similar to the previous two ideas. They're kind of, once you see them, they're like, yeah, they're quite obvious. So here's the idea. What we do is the pre-trained model, the weight related to a pre-trained model. Here's this illustration for just one, as there's only one weight matrix, but you will have lots of these, right? And also, you can apply this only for one layer, or you could apply to multiple layers also. The idea is kind of specific to per layer, okay, in the sense that you could apply to multiple layers or one layer, doesn't matter. I mean, that's something you need to decide. So what you do, the model that is already trained before, that weight you'll keep it fixed. Okay, let's say it's D cross K, that weight matrix. Let's say we are focusing on the weight matrix. This D cross K. Then what we're going to do is basically work with another pair of matrices, B, A, and B, whose sizes are D cross R and R cross K. Okay. So A and B are two additional matrices that we're going to work with in our fine-tuning step. So this step is already there. We already have the original weight. Okay. We're going to now create two new matrices with random, with which we want to tune for, such that their dimensions are D cross R and R cross K, where D is the same as D here, K is the same as dot K over there. So what is R, right? So R is basically a number which is much smaller than minimum of D and K. Okay. So R is, think of it as 2 or 3 or 5 or something. It's really small compared to some of these weight matrix sizes that you would see, right? For example, even the illustration over there, the weight matrix, this illustration here, right? This weight matrix here is taking potentially 100 dimensional input and producing 100 dimensional output. So it's 100 cross 100. Okay, so a D and K would be 100 and 100, whereas R can be like 2 or 5 or something. Okay, really small. Where did the presentation go? Oh, yeah. So now what we're going to do is, in the forward pass, okay, very simple idea. The forward pass, when we get some input vector, we're going to basically multiply W times X. We're also going to multiply B, multiply with A first and then B next, okay? So that the dimensions match, and we still get a D-dimensional vector output. Okay. So here, when we multiply a K-dimensional vector coming from here, we'll get a D-dimensional vector as an output here. And here again, if we multiply with a K-dimensional vector, we'll still get a D-dimensional output here. Okay. Okay. Don't worry about the dimensions, in the sense that originally we had the sum vector was coming in, we had to get some dimension out, right? These two matrices, because they're relying on the same two numbers, except for the R, just multiply appropriately so that, yeah.
For normal matrices multiplication, we used to take a common R.
No, these are two matrices. I mean, why are we focusing on this? Is because this is called a low rank approximation to a matrix which is actually D cross K. Okay. So what would you do? So let's say if you did not have B and A, let's say you had W prime. Okay. So how would you do fine tuning in that way? If you had a W prime, you would say, oh, I have some original W, I don't want to change it. Let me just change W prime just the weights of W prime such that I can predict well. Okay, it's like saying so what's the difference? What is W prime doing, right? So when I'm doing a forward pass, I'm going to use both W and W prime and then produce an output. So what do I mean? So if you have X as an input, instead of Wx as an output or Wx plus B as an output, I'll have W plus W prime times X plus B as an output. Okay, so it's as good as saying I have original W, I'm not going to touch it. I'm going to create another W prime. I'm going to add those two together. That's going to give me a new combined matrix, and that I'm going to multiply with X, and then I add B and then pass it forward, right? So it's just decoupling. It's just trying to preserve that, okay, if something was trained from before, let me not touch those numbers. Let me preserve those numbers, and I have an additive correction, additive numbers, which is tuned to my problem, okay? Which is tuning to my problem, okay? So instead of tuning the original numbers, I'll keep them fixed, but I'll be using them in forward passes and whatnot. But what numbers I will actually be changing are numbers which are of the same dimension as this W. Okay. Now, instead of keeping one W prime matrix, I'm going to decompose it as a product of two matrices, which are both low rank. Okay, since R is low, the rank of a matrix is the lowest of the two dimensions that it has. Okay. So if R is, let's say, 5, if even D and K are 100, the ranks of B and A are considered 5. Okay. And the number of numbers needed to represent B and K are going to be 5 times 100 and 5 times 100. So 1,000 total. Whereas if you had 100 cross 100 matrix W prime, then you'd have 10,000 numbers. Okay. So you have 1,000 numbers versus 10,000 numbers. You had parameter reduction because you're making a low rank approximation of potentially a bigger matrix that you could have worked with. Okay. So the whole idea is not to just work with some W prime and just keep it and not consider its rank. To explicitly say that it could be low rank, I'm going to make that assumption. That's in that way, I just need to tune a very few number of parameters. Okay, that's the whole idea of this tuning approach, is to kind of reduce the number of parameters that I want to tune while I'm doing fine tuning. I'm still relying on the original model, and I'm only going to tune some additive corrections to it, whereas those corrections are basically correspond to a low rank approximation of potentially a bigger matrix. Okay. Any questions or confusion here?
What about that loss?
Yeah, because these are the only things that are where your gradients are computing and so on. These are untouched. I mean, these are frozen. Yeah. So loss will be on. Oh, when you do a loss, you have to take W plus this matrix. So the forward pass is always the same, right? So you have to change the weights. That's the whole point of fine tuning. You have to change the weights of the pre-trained model. We are changing the weights by saying, okay, we'll retain the original fine-tuned model base as is, plus add some correction to it. If I sum them up, now I have changed weights, right? It's just that these weights will be learned through minimizing the loss. Yeah. It's the same loss. This is exactly the same CNN or any sort of like cross entropy loss or whatever it is. Yeah. So the benefit is basically less parameters. Okay, and there are a few other that are written, but it's basically just less parameters. Okay, so let's actually there is a this is, I guess, a snapshot from the paper that introduced this, but let's actually go back to this idea, and I have a notebook here. I want to kind of just show how simple it is. So Torch Vision is that extra package in addition to Torch that helps you easily load a pre-trained model or a data set or a few other things. And you'll see this actually in assignment 2. There's a starting code for this question on fine-tuning or whatever transfer learning in assignment 2. You will see the same pattern. Okay, so this is just, think of it as like just a warm-up for that pattern. Okay, so first set is the datasets object is actually lets you load MNIST very directly. You don't have to download MNIST and read from directories and whatnot. It turns out that the datasets object in the Torch Vision package, you can actually directly get MNIST data. Okay, so that's how we're getting the MNIST data. Okay, this data, it's a certain. You should look at the types of these objects. Okay, so the MNIST train set is of the type dataset object. So dataset is a certain type in Torch. It lets you, so it's a certain type, which basically is just a very simple dictionary, behind the scenes, but it's basically helps you remember like which class, what is it. Let's say if it's an image, you don't have to read the image beforehand. You can keep it at disk, but just know that this file name corresponds to class 1, this file name corresponds to class 2, so that you don't have to load all your image data at the same time. Okay, that makes sense, right? If you have a million images which are all high res 1 megapixel each, then you can't really load all of them at the same time, right? So that's what a dataset object does. And then the data loader object helps you iterate through this data set. So data loader is really enabling you to sample a batch of five images from disk, read the file names, read the files from disk, and actually pass it to the model if you want. Okay, so that's what a data set and a data loader do. Maybe I'll discuss this again next lecture because it's going to be useful for your assignment. So anyway, load the data and choose the device to be a GPU here. It doesn't matter for us. So here is the, that person called this rich boy network, in the sense that this is a more expensive network, okay, to classify MNIST digits. So it has a linear layer, another linear layer. So this is exactly what you did in assignment 1. Okay, I don't want to, you used Keras and TensorFlow, but it's basically the same. It's just a bunch of linear layers, and they're applying, they're first of all making it linear. They're making it vectorized. So instead of view of -128 times 28 is just reshaping it to be a really long 784 dimensional vector, and applying linear layer first, applying a ReLU, applying another linear layer, applying a ReLU, finally the output layer to produce a 10 scores. Okay, and that's it. So that's the network, and there's a training loop. I think this is something we can parse later. Okay, so let's not. I was just showing some things last time. Yeah, so let's say there's some training and we were able to learn that weights of that network. Okay, so what you can do is you can. So for this fine tuning step, this is an illustrative notebook. So for the fine tuning step, what we're going to do is we're going to remember the original weights. Okay, so how do you remember the original weights? There's a simple for loop here to kind of say, oh, what were the parameters? Let me just put them in a dictionary. Okay, that's what we're doing. And then you can remember. You can also print a test performance of whatever model you created. Here, the test performance is written in terms of how many mistakes did you make. It's like the confusion matrix, but you're just aggregating the off diagonal entries basically. So how many times did you make a mistake when you're trying to recognize 0? How many times did you make a mistake while recognizing 1, and so on. So anyway, so that's just some performance of an original network. Now, what you can do is we're going to introduce these low rank matrices. Okay, so how are we going to introduce this? So originally, okay, so before we introduce, we're just trying to see how many parameters are there in layer 1, layer 2, layer 3. So this is the sizes, okay, of layer 1, layer 2, layer 3, as in like the 3 linear layers. So the total number of parameters in the original network is 2 million. Okay, it's a lot, right? So just for simple MNIST data set, it's a lot of numbers. But this is 2.8 million, okay, number of parameters. Now what we're going to do is add these extra low rank matrices. So we'll create a so this is how you define a parameter. Okay, so let's not worry about very specific implementation details, but this is how you define the A and B matrices, where you can define the rank to be some low number. Okay, that way you have number of numbers to be low. And in the forward pass, what you're going to do is use the original weights plus the low rank and the low rank, their product, with whatever is original. You need to reshape it appropriately, and that's the matrix you want to use if you're going to use the low rank approximation. Low rank fine tuning process. Okay. So what I mean, so this is just a step where they're saying that if low rank is enabled, then use the original weights plus the new matrices whose weights you're going to learn through the backdrop process, training process. Use them, and if it's not enabled, just use the original weights. Okay, it's just a simple trick of keep the original weights or use original weights plus the low rank approximation. And then once you have that thing, you can change your change your network so that you're going to use this low rank part in your linear 1, linear 2, and linear 3 layers. Okay? Those are 3 layers in your network. You can change it to use these use this approximation. You can replace them with this approximation. Okay. So the way you enable disable LoRa is also given here. Just, if you set dot enable is true, then you enable low rank approximation. Okay. Now let's look at what's happening, right? So we already saw the printout for these four lines, which was the original network was 2.8 million number of parameters. Okay. Now with the LoRa approximation for all these 3 layers, these 3 matrices, we have number of parameters introduced is actually only 7,000 or 6,000, 7,000. Okay. And so the total number of parameters, so when you're fine tuning, you're only touching 6,000 or 7,000 numbers. Okay. Whereas if you think of the fine tuning process I was showing in the slides before, the fixed feature extraction versus fine tuning, if we set some learning rates for some really low learning rates for the entire thing, there's so many parameters. Okay. Everything is going to be updated. Okay. Whereas here, the original parameters remain fixed. You're only updating the A and B entries, but A and B are like tall and wide matrices, so that the number of entries is actually like 7,000. Okay. So the number of parameters is showing that 7,000 divided by 2.8 million is some small number, but that's what it is. So after training, and this is just an illustration, though it probably doesn't show any huge performance improvement, but you can do some training. And oh, I don't even print the performance here. I didn't run it recently, so yeah, I mean, unfortunately, no performance here, but yeah, I mean, I could try to run it. Let's try. Yeah, it's 8:23. Let me not try to do it something last night. But this is the new idea. Okay, so the idea is basically just this. So to fine tune, you're basically fine tuning W plus W prime. You're only touching the W prime, where W prime is defined to be equal to B times A. Okay.
And things. For example, like the code you showed.
Yeah.
So we are just expecting that after this fine tuning, for example, there was a lot of mistakes in identifying the number 3.
Yeah.
So probably it would be better in identifying. Could be.
Yeah, if you maybe sample more of that data and try to tune it.
And second thing, when if you can go to the code again.
Yeah.
Where we were adding the matrices A and B.
Yeah, so we added so the way we did it is a very nice way where he wrote it once and then he added it to all the 3 layers together. Yeah.
I like this one, like we started considering that the multiplication is 0 at the beginning of the training.
Where did it say that?
And 0 for like the B matrices we have taken a
we use a random Gaussian initialization for A and 0 for B, so the grain so the correction is 0 at the beginning of training. That's just something from the paper. Okay, there's a paper that proposed this process. Okay, but the process, the key point is not so much about the initialization.
I would say some details start from 0 and then increase on the matrix multiplication, like the weights that we are lost will be calculated.
Yeah, so this will be providing 0, so it will not change the when the x is being multiplied with this W prime, which is B times A or delta W here, yeah, that root will be 0. So the prediction will be as good as the original model. It's basically the same as the original model prediction. It will have a loss. Okay, that loss will be backdrop to update these B and A values. Okay, so yeah, even if the initialization is that the numbers can be changed. Okay, it's not an issue. Yeah. Anyway, just to summarize, we saw for the second part, we saw 3 things, all under the umbrella of transfer learning, or basically fine tuning, or basically saying the same as using pre-trained models to adapt to your use case or application. First one, fixed feature extraction. Second one, very simple relaxation of that, which leads to fine tuning. Third one, something called LoRA, just has a low rank adaptation, which just makes sense for really large models, because in that case you can't really tune everything. all it's saying is just have correction matrices which are low rank. And so how do you represent correction matrices which are low rank? Explicitly represent them as product of two low rank matrices. That's all. Okay. Any other question? Yeah. So what we'll do is next time we will pick back up from there and talk about some of these tricks. Okay, they are actually very interesting to learn also. And in fact, there's a link in this lecture goals for this lecture 3, which is about dropout. But I'll discuss that link next time. Okay. The link is inside. There's also a code example discussing the details. Okay, thank you.